Hello, so today we will still be learning about the Markov chain, but today we will learn about the n-step transition probabilities and probability distribution. Just let me make it clear to you what exactly are we talking about. Okay, because when we had learned about the transition matrix, we had mentioned that it is the probability. Okay, the transition matrix consists of probabilities. The probabilities that the state changes from AI to AJ, from one state to another. Okay, but when we were calculating it when the state changes in one step only. Okay, for example, we had seen an example yesterday. Just let me show this one again. We had seen this one. A man was either driving or was taking a train. Okay, we had calculated the transition matrix, but that transition matrix that we had calculated was only for one day. Okay, what I mean to say is one day or one round or one step. What I mean to say is, suppose on the first day he takes the train, on the second day he drive. Then when we were calculating the transition matrix, we were just considering the two consecutive days, okay, or two consecutive trials, okay, in one step only, that is from the first to the second. Okay, so we had denoted by PTD the probability that the person will switch from train to driving in one step. Okay, but what if we want to find the probability that the person switches from a train, okay, to driving in 3 steps or 4 steps or 5 steps? Okay, so if you are noticing, okay, it is very complicated indeed, because on the first day, okay, he may take the train. On the second day, again he may drive or take the train, and the third day again he may drive or take the train. Okay, so we are having so many cases. Okay, so these possibilities keep on increasing day by day. Okay, so that is why just by using the transition matrix, we can calculate easily. Okay, for this we need a theorem. Okay, but for now, okay, I will introduce a notation. Okay, maybe I will just write down as a note. Okay, note when calculating the transition, okay, when forming the transition matrix, matrix P, then Pij is the probability that the state changes from state AI to state AJ in one step. Okay, so when we were forming this one, we were only considering one step. But now what we will do, we will use a notation, okay, which will help us. Notation. Pij, okay, and over here on top I will write n. It is not power n. Okay, it is not power n. That is why I have kept it inside a bracket or parenthesis. This one will be used to denote, the probability that the state changes from AI to AJ in n steps. Okay, but okay, calculating this probability, it may be a bit difficult because we have to consider so many cases. The first day, just like we had seen, he may take the train. The second day, he may drive or take the train. The third day, again, we have so many possibilities. That is why we need a theorem how to calculate this one so that it will be easy. Okay, this is the theorem. If P is a transition matrix, if P is the transition matrix of a Markov chain, then okay, we can raise this power to P power n. Then P power n is the transition matrix in n steps. Okay, or it will consist of n step transition probabilities. Okay, maybe I will just write down over here Pij power n, not power n, Pij, above we are writing n, is called the n step transition probability. Okay, so over here we have this theorem, that is Pij, over here we are having n, it is just a notation, it is equal to the ijn entry of P power n. Okay, we will prove these theorems afterwards, but for now let us just look at some exercises. But again, before looking at the exercises, I will just explain to you about probability distribution. Okay, again, I will explain some more about this also when we are reaching. Okay, so when talking about transition probabilities, we are always mentioning that the state changes from one state to another state. Okay, so when a state changes from one state to another state, we are using transition probabilities. Okay, but what this probability distribution, it is different from transition probabilities. Over here, we are not considering any more change. Okay, we are simply calculating what is the probability that the system will be in state in one state. Okay, we are calculating that. Okay, again, I mentioned over here, okay, when we are dealing with transition probabilities, a question may be asked in this way. What is the probability that the state changes from AI to AJ, that is from one state to another state? Whereas over here in probability distribution, the question will be something like this. What is the probability that the state is in AI? Okay, what is the probability that the state is in AI? Okay, so that is what we are asking. Okay, there is no more change from one state to another. We are simply asking the probability that the state will be that the system will be in that state. Okay, so let me just write it down. If A1, A2 up to AN is the state space, that is the possible outcomes, then P1, P2, Pn is called probability distribution where Pi is the probability that the state, that the system is in the state AI. Okay, so P1, it is the probability that the system is in the state A1. Okay, for example, okay, yesterday I was giving you an example about a person moving in a grid, right? When we were calculating transition probabilities, we were calculating what is the probability that he will change from this position to this position, or from one position to another. Okay, so that is about transition probabilities. But when dealing with probability distribution, okay, we have to start somewhere. Okay, when we are performing this experiment, we have to start somewhere. Okay, so at some instant of time, there will be some probabilities attached to each of these possible states. Okay, so those probabilities that are attached, they are called as probability distribution. Okay, the whole thing, it is called as a probability distribution of the system. Okay, so again, okay, so the probability distribution, it will change. Okay, maybe at the first step it will have a different probability distribution, that is, these probabilities will all be different. After another day, or in the second time, this probability distribution will again change. Okay, so we can have so many probability distribution depending on the steps: first step, second step, 3 steps. Okay, what we will do over here, okay, so usually what we used to do, we will have some sort of a initial probability distribution. Okay, no, over here I'm writing P0, do not make any confusion. This one is not P power 0. Okay, it is just a notation. Okay, P1 0, P2 0, up to Pn 0 is used to denote the initial probability distribution. Okay, when we are doing the examples, it will become clearer. Okay, what exactly we are talking about. Okay, so just like I said, these probabilities will change after one step, after 2 steps. Okay, but again, calculating all of these probabilities will take time. Okay, and it may be difficult. Okay, especially if it is a very complicated process, then it will take a lot of time to calculate this. Fortunately, we can use the transition matrix to calculate the probability distribution after n steps. Okay, Pn, okay, P1n, P2n, Pn is used to denote the probability distribution in n steps. Okay, so let us just again, how will we calculate this one? We will have to use a theorem which involves the transition matrix. So another theorem that we can have is this. Okay, we will do the proof for all of these theorems again afterwards, but for now let us just take a look at the statement. If P0 is the initial probability distribution, and P is the transition matrix, then what can we have? Then Pn, the probability distribution in n steps, it will be equal to P0 p power n. Again, do not make any confusion. This one, it is not p power n, it is just used as a notation. P naught, again, it is not p power 0, it is just a notation for the initial probability distribution. And p power n, this is indeed a power, okay, p power n. Okay, we are raising the matrix to the power n. Okay, for example, that is, okay, p1, if we are calculating p1, it will be p naught, p power 1, which is p. Okay, what about p2? p2, it will be p naught, p squared. Okay, but p naught p, it will be p1, so it will be p1 p. Okay, similarly, p3, you can obtain it to be p2 p. Okay, and so on. We can actually do this. Okay, you can go on infinitely. Okay, p3, p4, p5, p6, p7, p8, p9, and so on. Okay, so now that we have discussed those, let us just take a look at these examples that we will do today. Again, okay, it is something that we had done before, okay, but I had added some extra questions. Okay, question number 1, we had already seen this question. Refer to the link in the description for the video, how do we find this transition matrix. Okay, but you can see the red mark over there. If initially the person takes a train only if a 1 or a 5, okay, if initially the persons take the train only if a 1 or a 5 appears on rolling a dice, then find the probability that he will drive after 4 days. Okay, so what is happening over here? So we are having this situation where a person will either drive or take a train. Okay, but he will have to start at some point, right? So at some point of time, okay, maybe he is just starting his work. Okay, he is thinking to himself, what should I do? Should I take a train or should I drive? Okay, he cannot decide. So what he does is he just roll a dice. Okay, 1 2 3 4 5 6. Okay, if he roll a die one time, if 1 or a 5 appears, according to the question, then he will take the train. Okay, so initially if 1 or a 5 appears, then he will take a train. Okay, so let us do this question 1. Solution. Okay, the transition matrix is P. Okay, again, how do we find this one? dt. Okay, we can write it as td. It really doesn't make any difference. Okay, of course the numbers will change, but overall the result will be the same. Okay, so how did we find this one? Suppose he never take the trains 2 days in a row. So if he takes a train on the first day and on the second day will never take the train, and equally likely, refer to the link in the description. How do we find the transition matrix? Okay, so the transition matrix is this. Refer to the link in the description for the video. Next, what will we do? Okay, so if you see, the question is find the probability that he will drive after 4 days. Okay, so it doesn't say anything that he will change from train to driving or from driving to driving again. It simply states that we need to find the probability that he will drive after 4 days. Okay, so we don't know what happened on the first day, second day, third day. Okay, it just asks us to find the probability that he will drive again after 4 days. Okay, so let's see. For that, okay, since it is not relating to the change, we will need to find P4. Okay, we will need to find P4. I hope that is clear. Okay, but to find P4, we will need the initial probability distribution. Okay, first we find the initial probability distribution. okay, which is P naught. Okay, so the initial probability distribution, he can either drive or take a train. So it will be something like this: PD 0, PT 0. This is the initial probability distribution. Okay, now again, how do we find this one? We will have to use what is given. He takes the train if 1 or 5 appears. Okay, now, okay, PT 0. Initially he takes the train if 1 or 5 appears. Okay, so 2 possible cases out of 6. Okay, because on rolling a die, the possible outcomes are 1, 2, 3, 4, 5, 6. Okay, so if 1 or 5 appears, which is 2 of them, 1 and 5, then 2 out of 6, okay, he will take the train. This is initially, which is 1 by 3. So what about PD? PD 0, it will be 1 minus 1 by 3, which is 2 by 3. Okay, so that is how we find the initial probability distribution. Okay, this is a very simple exercise. Maybe we will encounter some more difficult exercises later on. Okay, but this is how, for now, how we find the initial probability distribution. Okay, so now what we will do, now we will find P4. Now, P4, since we need to find that he will, okay, what do we need to find? We need to find the probability that he will drive again after 4 days. So we need to find P4. Okay, after 4 days, 4 step. Okay, so this one, it can be written as P3P. Okay, but also P3, it can be written as P2P. P2P, it can be written as P1P, and P1P can be written as P0P. Okay, so if you are seeing this pattern, okay, I will just write this one in square brackets. We first need to find P1, then we can find P2, we can find P3, and finally we can find P4. Okay, so you may be thinking that, okay, we can simply use this P0, P power 4. Okay, but I don't suggest you to use this one directly, because over here you will be taking the matrix to the power 4, okay, which can be very difficult. Okay, it will take you a lot of time to raise the matrix to power 4. Okay, so we have found out P0. Okay, P0, it's equal to, okay, first it was PD0, PT0, and okay, PD0, we have seen that it is 2 by 3, 1 by 3. Okay, you have to be very careful in this order. Okay, the matrix P that you are considering should also be D first and then T. That is why over here I am writing D and T. If suppose you are writing T first, then over here also T first will be written. Okay, PT will be written first if it is the other way. Okay, so now let us find P1. P1, it will be 2 by 3. It will be P0, P. P it is 1 by 2, 1 by 2, 0, 1. Okay, or how much was it? Never takes the train 2 days in a row. It's 1, 0. Okay, so this is how we calculate. Now we can just simply find 2 by 3 With this one it will be 1 by 3 plus 1 by 3, and over here will be having 1 by 3. So P1 it will be 2 by 3, 1 by 3. Okay, now we can calculate P2, which is P1P. It is equal to 2 by 3, 1 by 3, 1 by 2, 1 by 2, 1, 0. So you will be having 1 by 3 plus 1 by 3, and over here you will be having 1 by 3 again. So we are getting the same thing. Okay, sometimes it may differ, okay, but over here we are getting the same thing. So over here we're getting 2 by 3, 1 by 3. Again we are having the same thing. P3 also will be the same thing. Okay, P3 similarly P3 equal P2P will be equal to 2 by 3, 1 by 3. Afterwards, okay, we can finally find P4. Okay, after this, I'll write it here. P4, it will be P3P. Again, this one it will be after substituting these values, 2 by 3, 1 by 3, and P which was 1 by 2, 1 by 2, 1, 0. Again, you will be having 2 by 3, 1 by 3. Okay, so this is what is happening. Okay, but the question asks you, what is the probability that he will drive after 4 days? Okay, this is the probability that he will drive and take the train after 4 days. Okay, hence probability that he will drive after 4 days is equal to 2 by 3. Okay, so this is the required solution for number 1. Okay, now let us do question 2. It won't take too much time. Okay, the transition matrix is okay, let me just write it down. We had already seen how to calculate the transition matrix. Again, you can refer to the link in the video in the description. Okay, A always throws the ball to B. Okay, so A always throws the ball to B. Okay, so A always throws to B. So you'll be having 0, 1, 0. B always throws to C. B always throws to C, so 0, 0, 1. And C is just as likely to throw the ball to B and to A. 1 by 2, 1 by 2, 0. Okay, so it's equal. Okay, and the sum should be equal to 1. Now, what do we need to show? If you see the question, what is the probability that the ball switches from A to C? Okay, so if you notice this question number 2.1, it asks you to find the probability that the ball switches from one state to another. So we are involving two states, and we need to find the probability that it switches from one state to another. That is why we will need the n-step transition matrix. But this one is after 2 rounds. So for number 1, we will need to find p squared. Okay, we will need to find p squared because that will give us the transition probability in 2 steps. Okay, so p squared will be 0, 1, 0. We can multiply them out. 0, 1, 0, 0, 0, 1, 1 by 2, 1 by 2, 0. So after multiplying, we will be having 0, 0, 1, okay, 1 by 2, 1 by 2, 0, and for here we'll be getting 0, 1 by 2, 1 by 2. Okay, so now we have found p square. But again, okay, so how did we know that we have to find p square? Again, because there is a change from one state to another, and also in 2 rounds. Okay, but now the question is asking us to find from A to C, right? From A to C in 2 rounds. From A to C. So it will be related to this entry. Okay, hence we have found the solution. Okay, again, probability that the state changes from A to C in 2 rounds. A to C in 2 rounds, which is square, so it will be equal to 1. Hence, probability that the ball switches from A to C in 2 rounds, it's equal to 1. Okay, so it's certain that the ball will be reaching C in 2 rounds. Okay, from A to C. Okay, it will switch from A to C in 2 rounds. That it is guaranteed. Okay, that if initially the ball was in A, after 1 round it will be somewhere else. Okay, but this is actually very interesting. Okay, just take a look. Okay, so it is guaranteed that after 2 rounds the ball will reach from A to C. Okay, just take a look. Firstly, A will always throw to B, right? So after 1 round the ball will reach to B. B, according to the question, it always says that B will always throw to C, right? So after 2 rounds, from A to C, it is guaranteed because we are having probability 1, which is also which can also be seen logically just by doing something like this. Okay, but if it is 5-6 rounds, okay, doing it like this, it may be complicated. That is why finding the power of the matrix and then finding the probability will be easier. Okay, so that is about question number 1. Okay, now let us take a look at question number 2. Question 2, it says, if initially the ball is with B, what is the probability that the ball is with B again after 3 rounds? So this question number 2, it is about probability distribution because it doesn't involve any change of state. Compared with question 2.1, it involves a change of state from A to C, but question 2.2, it doesn't involve a change of state. So we are talking about the probability distribution. So after 3 rounds, that is, we will need 3. Okay, so initial probability distribution, we can denote it with P1, P2, P3, okay, but it will be simpler since the states are A, B, and C. So we can denote it with P0, PA0, PB0, and PC0. Okay, initially the ball is with B if you are not seeing the question. Okay, if you are not seeing the question, initially the ball is with B. Okay, so 0, the ball is not with A, it is guaranteed that the ball is with B. So this is the initial probability distribution. What is the probability that okay, after 3 rounds? Okay, so now we will need to find P1. P1, if you remember, it is P0P. P0 will be 0, 1, 0. And P, it is the matrix 0, 1, 0, 0, 0, 1, 1 by 2, 1 by 2, 0. So over here we are having 0, 0, 1. Okay, so this is what we are having, P1. P2, it will be P1, P. P1 it is 0, 0, 1. Okay, we are interested in 3 rounds. Okay, 3 rounds, so that is why we will be calculating up to P3. 0, 1, 0, 0, 0, 1, 1 by 2, 1 by 2, 0. So over here we'll be having 1 by 2, 1 by 2, 0. Okay, so lastly we can find out P3. It will be P2P, which is 1 by 2, 1 by 2, 0, 0, 1, 0. Okay, so how much will it be? 0, 1 by 2, 1 by 2. Okay, so this is the probability. Let me just repeat what we are finding. This is P2, right? So this is the probability that the ball is with A after 2 rounds. This is the probability that the ball is with B after 2 rounds. And this is the probability that the ball is with C after 2 rounds. Okay, now let us take a look. Okay, after 3 rounds, okay, this is the probability that the ball will be with A, this is the probability that the ball will be with B, and this is the probability that the ball will be with C. Again, okay, we can actually do this. Okay, B. Initially, the ball is with B. B always throws the ball to C. So after one round, it will be with C. C will either throw to A or throw to B. So this is the second round. In the second round, after the second round, the ball will be with A or with B. The third round, in the third round, the ball will be with B or with C. Okay, so it's equal. Okay, equal chance. Okay, if you are noticing over here, there is an equal probability that the ball will be with A and the ball will be with B after 2 rounds. Okay, after 2 rounds, the ball can be with A or it can be with B. It can never be with C. That is why we are not having a picture like this, from C throwing to C. Okay, but this is what we require. Okay, hence probability that the ball will be with B after 3 rounds is equal to 1 by 2, which is this value here. Okay, so that is all for today. Until next time.